All right. My name's Oliver. And I'll be going over number one. Okay, so let's get right into it. Okay. Oop, my screen is bugging out. Okay. So first question. Give a tight asymptotic runtime bound for contains as a function of n, the size of the node. In the best case, worst case, and overall. Okay, so we have an int node class. So the length of the node is just going to be how many nodes it has, right? So if we draw out our linked list int node, so we can imagine this goes on till n, right? So this is going to be size of n. Okay, so let's consider our best case. So that is basically when we're considering our best case, we want to look for conditions that stop our method call early. So let's look at this if condition here, right? So if first is equal to value and the value is passed in as an integer. So this is a condition that is kind of independent of the size of our list, right? Because imagine if we pass in a very long list, or sorry, a very long int node, the value we're looking for could be in the first one, right? So let's say like we'd pass in a linked list of size n, and the first value is the value we're looking for, so it terminates early. So our best case is going to be like node.first contain value. So it's going to stop right away. And this is just going to be theta of constant time, right? Because it's just going to be doing one comparison and then it stops right there. So what about our worst case? So we are going to want to avoid the conditions that stop our method call early, right? So notice how we're making a recursive call right here. And we just want to avoid not having our node, or not having the value we're looking for inside of our node. So say our best case condition is the list doesn't contain value. So let's draw out our recursive call frame, because this is a recursive method. So our input, so the size of our node linked list is going to be n on the first call, and then it's going to decrease to n minus 1, right? Because we're taking the rest and calling contains on it. And then again, it's going to be n minus 2. We're just going to decrease by 1 each time, all the way down to the bottom. Basically, when the length is 0, when our rest is null, right? So our call diagram here is going to be n tall, right? Because we're making those n calls. And we're going to stop when we hit our condition rest equals null. So now all we need to figure out now is how much work is being done in these calls. And it's just going to be constant, right? Because every time we're just checking some Boolean conditions and then making a call. So there's really no work being done in terms of n. So it's just going to be constant, right? So the work at each level is 1, and we have a size entry. Since the work at each level is the same, we can just multiply the work done at each level by the height, which is going to be n times 1. So that's going to give us our best case runtime bound is theta of n. And if we were to summarize that in kind of one expression, that would be big O of n, because we kind of think of this method going up to linear time, but it could run in constant time if our value is found in the beginning, right? Oops. So it's kind of a good way to summarize it, right? Okay, so let's move on to the next one. F. Give a tight bound in the overall runtime of the following function. Okay. So we have our base case here, n equals 1, right? So this is actually going to be irrelevant to I guess like it's not going to stop prematurely because we're assuming n is very large. So this is just going to be our base case for the purpose of making sure our function actually works correctly. Then we're creating a variable y, and then we're going to loop up to input n linearly, right? Because x is increasing by 1 each time, and we're just going to add 1 to y. And then in the end, we're going to be making 2 recursive calls and then adding y. Okay, so before we even get into like a car diagram, let's kind of figure out how much work is being done in terms of the input to f, right? So say we input just the number n into our function, right? Just for this call, how much work is being done, right? That's what we want to figure out. So in terms of n, it's going to be, well, we're doing a for loop here, right? And x is going to be increased by 1 each time. So we're doing x is going to take on values 0, 1, 2, up to n minus 1, right? So we're actually going to be doing linear work in terms of n, our input, right? So the work done, if our input is n, is going to be n work. So what if our input is, say for this call specifically, our input is n over 2. How much work is going to be done in that call? That's just going to be n over 2 because x is going to start at 0 and go all the way up to n over 2, right? We're assuming that the input is n over 2 now, right? So this is going to be helpful for our call diagram. So let's start making our call diagram now. So our first input is going to be, assume is going to be a very big n. So like we just said, the work done at the input is just going to be linear to the input, right? So if you input n, we're going to be doing n work. So then f makes 2 recursive calls, right? And we're going to divide by 2 each time. That's going to be n over 2, n over 2. So then we do n over 2 work, right? Because it's linear in terms of our input. And then these are going to be making 2 calls. The inputs are going to be n over 4, same again. Right. Okay, so it's just going to go all the way down until we hit n equals 1. So what we're actually doing here is we're decreasing logarithmically, right? Because we're dividing by 2 each time. So the total height of our call diagram is actually going to be log 2n, right? Because every time we go down to the next layer of the call diagram, the tree, we're decreasing by 2. So we're going to go all the way down to 1. So we're going to have log 2 of n. So now let's figure out how much work is being done at each level, right? So level 1, we're going to have n work. Level 2, we're going to have n over 2 plus n over 2 work. That's just n. Level 3, we're going to have n over 4 plus n over 4 plus n over 4 plus n over 4. That's just n over 4 times 4. And that's just going to be n. So notice our pattern here, right? Every call or every level in our tree diagram here is just going to be n work. So since every level in the call diagram is the same amount of work, we can just multiply that work per level times the height of our tree. We know the height of our tree is log 2 base n. Sorry, log base 2n. So it's just going to be n log 2n is our total work, and that's just going to be big theta of n log n. That's our final answer. Okay, so moving on to 1.3, Hippotype asymptotic bound for mystery. Okay, so we have 2 for loops here. We have I is going up to n squared, and it's going to be increasing exponentially, right? Because we're doubling on each time. So inside i's loop, we're going to have j, it's going to be going up to I, and it's going to be increasing linearly. Okay. So since we have a double for loop, I like to use the table to keep track of the values of I and j. So let's do that. J, and then work. Okay, so let's start with the I column. So I is going to start at 1, and then it's going to double each time, right? Because that's our condition right here. So I is going to go from 1 to 2, 2 to 4, 4 to 8, 4 to 16, and this is going to go all the way down to n squared, right? Because that's our stop condition in this for loop. Okay, so now we need to figure out for which values of I, what values of j is what values of j is going to take on. So in our inner loop, j is going to start at 0 and go up to I linearly. So for when I equals to 1, it's only going to equal 0, right? When I equals 2, it's going to take on value 0 and then 1. For 4, it's going to go 0, 1, 2, 3. For 8, it's going to be 0, 1, 2, 3, 4, 5, 6, 7. 16 is going to be 0, 1, 2, 15. And then n squared is going to be 1, 0, 1, 2, 3, all the way up to n squared minus 1. So since basically we want to count how many times system.out.print is being called. So we're kind of defining that as a cost model. So and this is actually associated to what values of j. So every value of j, for every value of j takes on, is actually going to be how many times print is called, because it's inside of the j for loop, right? So for our first iteration, I is equal to 1, j equals 0. So j takes on 1 value, so it's going to be 1 work. J takes on 2 values in the next one, so it's 2 work. And then j takes on 4 values, so it's going to be 4 work. And then 8 work, 16. And then for the last time, j is going to take on n squared values. So it's going to be n squared work. And then in the very end, we want to add up all the work in the final column. So it's going to be 1 plus 2 plus 4 plus 8 plus 16 all the way up to n squared. And this is our geometric sequence. So we only care about the last term here. So our runtime is going to be big theta of n squared. Right. Okay. So that concludes our rundown of these problems. If you have any more questions, you can email me at odpatrick@berkeley.edu. All right. Thank you.